All right, so let's go ahead and start talking about. All right, the first term we're going to look at is geosphere. And Kevin, would you go ahead and read for us the definition of geosphere? Okay, so grab a highlighter, highlight geosphere. All right, then on the layers page that we taped in, we're going to start with lithosphere. Highlight lithosphere the same color. Asthenosphere, mesosphere, outer core, and inner core. So whatever color you highlighted geosphere, we're going to highlight lithosphere, asthenosphere, mesosphere, outer core, and inner core. So the definition of geosphere is the solid portion of the Earth, and that's not really accurate. But whenever we came up with the term, that's all we knew. So the lithosphere is the layer that we're standing on, and obviously that is a very solid portion of the Earth. But as we go through these other layers and look at their characteristics, we're going to find out that that's not always the case. All right, the other one we're going to look at today is the atmosphere. So get a different color highlighter and highlight atmosphere. And on our layers page, we're going to highlight troposphere, stratosphere, mesosphere, and thermosphere. All right, geosphere is a solid part of the Earth. Alan, would you read the definition for atmosphere for us? All right, so we have a layer of gases that surround the Earth, and it's a mixture of gases. Of that mixture of gases, I bet you can tell me at least what's one component. So what's one gas that's in our atmosphere? Yes? Yes? Sure. Okay. A little. Yeah. Anything else? Sure. Anything else? Did you run out? Okay. So yeah, nitrogen and oxygen are the two that we're going to talk about. But sure, carbon dioxide, hydrogen, water vapor, pollutants, all of that stuff is also in our atmosphere. So do you know what percent is nitrogen? Or 73 or 74 or 75? Yeah, somewhere in the 70 mark. All right, so do you know how much is oxygen? Or 16 or 17 or 8 or 21? Pretty close. You were low on both of them, though. Man. All right, so make sure that you make note of the fact that our atmosphere is 78% nitrogen and 21% oxygen. So most of the atmosphere is composed of a gas that we really can't even utilize because we need nitrogen. It's very fundamental. It's very important. But we can't utilize it by breathing it in, and we'll look at that when we look at the cycles later on this week or next week. Oxygen, 21% oxygen. That's what we need in order to survive. And so you add those two together, you get 99%. That means everything else that was mentioned, carbon dioxide, water vapor, hydrogen, anything else that's part of the atmosphere, all composes 1%, that last 1%. So that's really not a whole lot. And that's where people kind of have that misconception that, well, carbon dioxide makes less than 1% of the atmosphere, so why is it so important? Well, that's why it's so important. Carbon dioxide makes less than 1%, so any little bit that we add on there. So let's say it's 0.7%. So if we double it to 1.4%, well, that's a huge increase in carbon dioxide. So we've got to watch those levels, and that's why that's important. Another really important gas in the atmosphere is ozone. So get you a third different color and highlight ozone. On the outside, we're going to give ourselves a note that O3 is the chemical formula for ozone. O2 is the oxygen that we breathe. So if the chemical formula is O3, do you know anything what that means? Sure. But what does it mean like about the molecule? There's 3 oxygen atoms. And so O2 tells us there's 2 oxygen atoms. So O3 is ozone. You breathe ozone, you die. Okay? Ozone is a pollutant. We don't want to breathe that in. O2 is oxygen. You don't breathe that, you die. Yeah, right, because that's 1 more oxygen, right? I mean, that seems like extra oxygen ought to be awesome. The problem is that molecule, the way it's bonded to create the O3, our bodies can't process that bond. So you breathe it in, it's going to stick to your red blood cells just like regular oxygen does, but basically it sticks to those red blood cells and takes up space because our body can't take that O3 and do anything with it. O2, the bond between those 2 oxygen atoms, our body can break that so that we can use the oxygen. So that, you don't breathe it, you die. This, you do breathe it, you die. All right. Ooh, that's a really good question. Hold on to that, okay? We're going to talk about it. So this is part of ozone, so I'm highlighting it the same color as ozone. And in fact, we haven't read the definition. Would you read the definition of ozone? All right, and so UV light, UV energy is actually bad stuff. So as we come to that here in just a little bit, we'll find out why ozone is so important and so helpful to us. All right, so now we are going to be on our little layers page. And we are going to start at the solid part of the Earth and work down first, just because that's easier. So, solid part of the Earth is the geosphere. The first layer of the solid part of the Earth, the first layer of the geosphere, is the lithosphere. Oop, bloop. Whoa, too much. Okay. All right, so the lithosphere, the width, if you would, the depth of the lithosphere can be anywhere from 3 kilometers to 300 kilometers. And that is a huge range. So a kilometer is probably about the distance of here, maybe to Lowe's. That's probably pretty close to a kilometer. But 3 kilometers in depth means from KTC to Lowe's, driving to Lowe's, back to KTC to Lowe's. I mean, that's that distance driving back and forth, uppy, downy. So, I mean, it's still pretty big distance. But our ocean floor is the thinnest part of the lithosphere, and that's probably that 3 kilometer mark. Mountains and landforms also are part of the lithosphere, and so that's where we get that 300 kilometer range. So the lithosphere is the part of the ground, the part of the crust that we walk on, and it definitely is solid. Well, yeah, I mean, the amount of traumatic experiences that would have to arise to turn it liquid would be a problem. The ground is lava? All right, so as we go further down into the geosphere, as we travel down, temperature increases. So it gets hotter as we go down. I have these little symbols. This is a red arrow up, a blue arrow down. I realize you don't have red highlighters, but I'm guessing a pink would probably work for you. This represents hot material rising and cool material sinking within the asthenosphere. So the lithosphere is solid, but the asthenosphere is sort of a putty-like consistency. It's not solid, it's not liquid, it's somewhere soft and squishy in between. The reason why it's kind of soft and squishy is because temperature is increasing. And so when we say that this is putty, that's rock material that is so hot that it's soft and squishy. No, I would not want to touch it. So I have uppy arrows, hot material rising, downy arrows, cool material sinking. These little circles, the arrows that form these little circles, they are forming a phenomenon called a convection current. So this is a convection current. This is a convection current, convection current, convection current. So the convection currents kind of work like the little conveyor belt at Walmart. You go into Walmart, you get your groceries, you put them on top of that little rubber mat. Cashier gets done with the customer in front of you. She pushes a little button and your little stuff takes a trip toward the cashier. Underneath that rubber mat, there's these little rope coasters, these little wheels, and they all turn in the same direction. Well, that's essentially the same thing that we have happening here. These convection currents are turning in one direction, and when they turn in the same direction, whatever crust is laying on top of them gets moved along like the little rubber mat on top of the wheels on the conveyor belt in Walmart. These convection currents are moving in this direction. These are moving the same way, and so they're moving the crust on top of it from the right to the left. Mm-hmm.
What part of the Earth would tectonic plates be?
That's a really great question, and hold on to that because we're actually going to talk about that vocab term. Just hang on. Let's get through these. Yes, just hold on. All right, so convection currents are movement of the putty-like material in the asthenosphere. The hot material rises because it's less dense, and when it gets over here to the surface, it cools it off, and then it sinks back down. Then it forms those little currents that move the plates on top of it. As we continue to go further and further down into the geosphere, temperature increases. But as you go further down into the geosphere, not only does temperature increase, but pressure increases too. So if you've ever been to the bottom of a really deep pool, all that water pressure on top of you, you can kind of feel that additional pressure. So imagine all of that rock material, whether it's solid or putty, pushing down. That creates a huge amount of pressure. If I have an ice cube is a solid. You add heat to that ice cube and it melts into a liquid. If I were able to look at the atoms of that solid ice cube, I'd see that they were packed really closely together. I heat it up. Atoms in a liquid, they have more energy. That gives them more room to flow, and so they have more space between them and they have more movement. Well, if I take that liquid and I compress it, and I add pressure to it, I make those atoms move back together and form into a solid. A good example of this is like natural gas, the propane for your barbecue grill. So the gas for your barbecue grill, when it runs through the grill and you light it, it's a gas, and you light it on fire. But when you go and you fill up that propane tank, they're filling a liquid into your tank because that liquid has been compressed. It's got a lot of pressure on it to keep it a liquid until you turn it on and run it through your barbecue grill. That's a different, hold on to that thought. That's a different kind of thing that we got going here. We want to concentrate on the fact that heat increases as we go down, and so does pressure. So there's a battle between the temperature and pressure in each one of these layers. When we get to the next layer, the mesosphere, there's so much pressure on it, it overcomes the increase in temperature, and this layer is a solid. Do we know for sure that this is a solid layer? Has anybody been down there, checked it out, take pictures? No, but we have some really good evidence, especially with our volcanoes and earthquakes, that give us an idea that this has to be a solid because of how those earthquake waves travel through it, the seismic waves. All right, so as we get further down, now the temperature takes over, and it overcomes the amount of pressure. And what does the little uppy, downy arrows represent? So the red uppy arrow represents hot material. The blue downy arrow represents cold. And the circle itself is called a convection current. So the outer core is somewhat liquid, and it also has convection currents. Those convection currents at this level don't move the plates on the surface of the Earth because those plates aren't sitting on top of them. These convection currents in the outer core are important because they create the Earth's magnetic field. And Earth's magnetic field helps to protect us from a lot of the radiation from the sun. So it's super important. So like UV radiation is cancer. Like having too much radiation from the sun would like fry us like a crisp. I mean, it would just like cook everything. There's too much. It's way too much energy. I don't think we would have a chance to. That's a really good question for another time. It's not like a fire burning. It's fusion. Wait. Fission, not fusion, fission. No. It's a nuclear reaction. So it's different. But see, and that's where I messed up. So nuclear reactions, they're actually fusion. The sun is fission, so it's breaking things apart. Or did I get that wrong again? I got that wrong again. The sun is fusion. Nuclear reactions are fission because you put a little molecule in there and it breaks them apart. That's what creates radiation. That's entirely another time story. Right now, we're talking about the outer core and the fact that the convection currents of the outer core cause Earth's magnetic field. So that's why I drew two little magnets here to remind me that it creates Earth's magnetic field. Then finally, the pressure overcomes the temperature and the inner core is solid. But the temperature of the inner core is estimated to be somewhere between 4,000 and 6,000 degrees Celsius. That's somewhere around 9,000 degrees Fahrenheit. So it's warm. But even though it's 9,000 degrees Fahrenheit, there are 3.6 million atmospheres of pressure pushing that material together and forcing those atoms to stay together as a solid. So that huge amount of pressure overcomes the temperature. That's a lot of pressure. We feel 1 atmosphere worth of pressure where we're at. And we don't really feel it because we're used to it. So, you know.
So what would happen, per se, if it wasn't all rough down there and it kept the pressure, the person was to, just pop in?
So if we go down in the bottom of the ocean, right? I mean, let's not even talk, let's just do something that we can kind of wrap our heads around. If we go down into the bottom of the ocean, can you just swim all the way down into the bottom of the ocean, or do you have to be in a submarine?
Even in submarines going down to the bottom of the Mariana Trench, which is the lowest point in any part of the world, it has just completely shrunk.
So can we swim down there, or do we have to be in a submarine?
You can't even get down there.
Okay, so can we get down to the bottom of an ocean? Let's leave Mariana's Trench out of it. Just by swimming down there, or do we have to be in a submarine? So can we swim there, or do we have to be in a submarine? Okay, so we have to be in a submarine. And you just said why? Because of the immense amount of pressure, and that's just water pressure. So that's not even the kind of pressure that they're talking about in these layers of the Earth. Yes, absolutely. Absolutely. All right, so now we're going to move up into the atmosphere. And the first layer of the atmosphere is the troposphere. The troposphere is this air right here. So we're standing on the lithosphere. We are walking through and amongst the troposphere. What did these little red arrows up mean? Yep, hot material rising, and the blue arrows down. And the blue arrows down. Cool material that is sinking. And so what did these little circles represent? Yes, convection currents. So we have convection currents that occur in the atmosphere as well. And the fact that we have those convection currents in the troposphere creates our weather. So all of that churning of the warm, moist air, cool air sinking, All of that movement creates the weather that we have. So the other layers of the atmosphere really don't have weather. Just the troposphere has weather.
Right, so what happens way up towards the ozone?
Hang on, we're getting to those layers. Boy, you are just full of questions today, aren't you? Okay, you have to hang on, we're getting there. I'll take that. All right, the next layer that we have is the stratosphere. What is in the stratosphere? No. And what's O3? Ozone. So the ozone layer is in the stratosphere. Pardon? Ozone layer. So there's tons of stuff that's going in all of these. I'm trying to simplify it so our brains don't bleed. I'm giving you what's important for each of these layers. Mostly the top of the troposphere, but I think the bottom of the stratosphere is like the when we're talking about commercial aircraft, I think most of them are the troposphere. I think there are some planes that go to the bottom of the stratosphere, but not very many.
I think any higher and they'll stall out.
Sounds good.
I think it's because they try to avoid the weather.
Well, yes, they definitely want to do that. All right, so the ozone layer. We said ozone down here, if we breathe it in, we're going to die. But the problem is that ozone is actually a really great molecule, and it gets a really bad rap because of the fact that we produce it down here as pollution. Down here in the troposphere, ozone is pollution, and it's bad. Ozone in the stratosphere is good. We want it there. Ozone is created by a natural process. When atmospheric oxygen gets hit by the sun's UV radiation, it turns it into ozone. So basically, when it gets hit by the UV radiation, it's absorbing the UV radiation. We don't want the UV radiation to make it down to us because it causes cancer. It'll do mutations in our DNA, and it can cause cancer. So this ozone layer is super protective, and it's very important, and we want the ozone in the stratosphere. That's where it's a good place to be. All right, next is the mesosphere. We had a mesosphere down here in the geosphere, and this one actually worked out pretty well because it's right there in the middle. We have a mesosphere. Meso means middle. We have a mesosphere in the atmosphere, and it's in the middle if we divide the thermosphere into two layers, which we kind of do. The mesosphere is the point in the atmosphere where the air starts to become so dense, the molecules are so close together, that anything that's going through it is going to cause enough friction that's going to cause it to burn up. So the trash, anything that's trash, whether it's rock, pieces of satellite that's falling through the mesosphere, it's going to catch them on fire. So if you ever go out and you see a shooting star, you're seeing that piece of rock or dust or trash or whatever that's going through the mesosphere, and it's hitting those molecules so fast that it heats them up so that they catch fire. So shooting stars in mesosphere. All right, so put pencils down for just a minute. I need to explain the thermosphere before you start drawing stuff in there. Because we actually divide the thermosphere into two layers. We divide it into the exosphere and the ionosphere. So the outermost part of the thermosphere is the exosphere, and that's where our satellites are rotating around the Earth. The bottom layer of the thermosphere, where it meets the mesosphere, that's called the ionosphere. In the ionosphere, there's a whole ton of little ions. They're little bitty particles. These guys get hit by the sun's radiation, and they absorb the radiation. So they're basically absorbing energy. They don't like it. Makes them too wound up, and they want to get rid of it. And the only way they can get rid of it is by asking questions. No, just kidding. The only way they can get rid of it is by giving off light energy. And so if you've ever seen the aurora borealis or seen pictures of it or actually seen it, that's what's happening, is all of those little ions are giving off all that excess energy because it makes them uncomfortable, and they give it off as light energy. In a sense, yes, because O3 is also absorbing stuff, but the O3 doesn't give it off. They're able to hold on to it, and it forms the bond to make O2 into O3. These guys don't like to hold on to it. They have to give it off.
Those ones are cooler because they have nice pretty lights.
I don't know. I really like ozone as well because it's keeping me from dying from skin cancer.
What's the side effect of the lights coming on?
There's side effect. There's
Is
no
there
side
any
effect.
bad part of them giving
Okay, hang on just a second. All right, you can go ahead and label thermosphere. Now, what did you ask?
Is there any like bad effect of them giving off that light, or is it just them releasing just pure energy? I feel like it gives them radiation off.
Well, so light energy isn't as dangerous as, say, the electromagnetic energy that they're absorbing. So I think actually the best way would probably say that I bet it's making that energy safer. Now, like I said, ozone hangs on to it because it's an O2 molecule, and that energy ends up being stored in the bonds to create O3.
So wait, it's just every time the O3 absorbs the energy, it's just making more.
So the O3 itself doesn't really absorb it. The O3 is created when atmospheric oxygen absorbs that UV radiation, and it stores it in a bond to make it through there. O3 is a product of oxygen and the energy from the sun. No, it forms a layer there. Now, we've done things to destroy it. We've put pollutants in the atmosphere that breaks it down and destroy it, but we don't want to do that. We want to keep it the ozone layer. Hold on to that question, too. We're going to talk about that. I'm telling you. You're my little ionosphere today. All right, so the asthenosphere is the part of the Earth that we're standing on top of, the solid part of the Earth. The lithosphere is the atmosphere that, where we're at right now. Bio means life. The biosphere is the part of the Earth where life is found. Some life can be found within the asthenosphere. So there are critters that live in the ground. There are critters that live in, not the asthenosphere, that's molten, sorry, my mistake. Lithosphere. So there are some critters that live within the ground. There are some critters that live up in the atmosphere in the layer of the troposphere. But it's a pretty narrow spot right here. So this would represent the range of the Earth that would be the biosphere. And the biosphere, put it back where it was at. Is the area of the Earth where living things are found. So the biosphere is extending into the ground, into the lithosphere, because there's critters that live in the ground. It extends into the troposphere, into the atmosphere above our heads, because there's things that live up there in the atmosphere. And I'm not even talking about birds and stuff like that. They're little bacteria that basically are out there in our atmosphere, and they're living things too, so they're part of the biosphere. So the biosphere is the area within the ground, on top of the surface of the Earth, and in the atmosphere where living things are found. All right, so I gave you a couple of sticky notes. These are going to go over your atmosphere because you can lift them up and still see what's underneath. And notice that the bottom of my sticky notes I have lined up with the bottom of the troposphere there. Yeah, I put it on the top. I don't know if it really matters. But I know, right? All right, so the entire reason why we have an atmosphere, I turn it sideways. So the entire reason that we have an atmosphere is because we have the force of gravity that's pulling those molecules, the little gas molecules, towards the Earth. So gravity holds our atmosphere. So other planets, the moon. There are some gases that surround the moon, but definitely not thick like our atmosphere is, because it doesn't have as much gravity as we do. Some planets have more of a gravitational pull, and so they have more gases that they're able to hold. When I think of air pressure, I always kind of think of it like a human pyramid. Down here, closer to the surface of the Earth, in the troposphere, there are lots more molecules of gas. The atmosphere is much more dense. The further up I go in the atmosphere, the fewer and further between the molecules are. There are less of them, and they're spread out much more. So when you think of it like a human pyramid, way out here there's a lot less air pressure in the thermosphere because at this point the atmosphere is much less dense. Closer to the troposphere, there's a whole lot more pressure because there's tons more molecules that are pushing down, or being pulled down actually, on that surface. So it's the atmosphere, this layer of the atmosphere, the troposphere, is much more dense. So that's why those little pieces of dirt and debris, they can make it through the thermosphere because there's not as many particles for them to hit. But once they get down here, that's when they start burning up and you see shooting stars because the density of the atmosphere is increasing. Oops, I think I forgot something. I did. So now we know where ozone comes from. Ozone's a natural process. The formation of ozone is a natural process. Nitrogen, most of the nitrogen that we have, that's coming from volcanic eruptions. We do produce some of it, but most of that's natural too. So the other important gas was oxygen. Where does oxygen come from? Where do we get the oxygen in our atmosphere from? You know this. Yeah, right? Plants. Is there anywhere else where we get oxygen from? Well, I guess that's good enough, right? No, where does the oxygen in the atmosphere come from? So how does it get into the atmosphere? I'm going to put that in the same category as plants, sure. What else? Say it again. Yeah, plants. Say it again. No, that's going to use oxygen, not create it. So where else do we get it from? Pardon?
Jump from them sometimes.
Oxygen?
It's not created by them, but it comes out.
Well, but that's what I want. I want to know what's creating the oxygen. No, it's not. Well, you said it's not, so what is it? It's not. In fact, plants don't even produce most of the oxygen in the atmosphere. Most of the surface of the earth is covered with water. So most of the oxygen that we have that's in our atmosphere is produced by critters like algae and little photosynthetic bacteria that are in those oceans. Algae is a critter.
It's a living being.
Yes. Sort of. Sort of. Yes.
I've killed so many people.
All right, so add this information. I told you to put your vocab up just a little bit so that we had enough room. And then notice I have that highlighted the same color as atmosphere. So most of our oxygen is actually coming from something other than plants. I'm thinking that most of the type we're looking at are protists. So, I mean, there are aquatic plants. There are aquatic plants. But the guys that we're thinking of are either protists or bacteria. And moss, yeah, I mean, moss is photosynthetic as well. Does it produce oxygen? Oh, yeah, okay.
That would make that thing a murderer.
Well, no. Well, yes, then we all are then, I guess. Y'all are making my brain bleed. All right, so